Hello again, guys. I'm back with the second video which relates to calculation of bending stress. If you recall, in the first video, I showed you how to determine the moment of inertia of an I-beam. Now, an I-beam is a symmetric cross-section, which we broke it basically into two flanges and a web. We just used the 112 BHQ to figure out the moment of inertia. But now, what happens if you have an unsymmetric cross-section? So there is symmetry, let's say, with respect to a vertical axis, but no symmetry with respect to horizontal axis. So in that case, we have to use an equation which is based on a theorem known as Parallax's theorem. So let me talk about this theorem, and then I'll show you how you can find moment of inertia of an unsymmetric cross-section. So what is this Parallax's theorem? It's really very simple. So basically, if you have an area, if you have a cross-section, so basically this is your cross-sectional area, this weird shape here. So it has certain area A, right? And then if you happen to know the moment of inertia with respect to the axis which passes through the centroid, point C, and then I bar, and when we use the bar notation, we basically mean that must be the centroidal moment of inertia. So the bar basically has to do with the centroid. Okay? And let's say so this is given, or you can get it from a table or something. And then let's say you want to find what? You want to find I with respect to the red axis. That's the unknown. How do we do that? You've seen this already in your statics course, but just to remind you about this theorem. Basically, if we know the distance d between these two parallel axes, so remember the black and red are parallel to each other, that's why it's called Parallax's theorem. So basically, if you want to find I with respect to the red axis, you say, okay, this I with respect to the red axis is equal to I bar, which is the centroidal axis, or moment of inertia with respect to the centroidal axis, plus the quantity of area times distance squared. Okay, so this is known as Parallax's equation. Just remember that you cannot do this for any two arbitrary axes, guys. So you can't say, oh, this is I1, this is I2, so I can say I2 equal I1 plus AD squared. That doesn't work. Okay? One axis has to pass through the centroid of the area for this to work. And typically now, if you have a rectangular cross section, that I bar is what? Is, as you've seen in the other videos or from tables, is 112 BHQ, where B is the width and H is the depth. And this is what we're going to use in the next page and apply this to our unsymmetric cross section. So let me move to the next page. So I have here an example of a typical T-beam, which is made of a flange here and a web here. Okay, and my objective is to calculate the moment of inertia with respect to the centroidal axis of this guy. So the first question we have is, where is the centroid of this guy? You guys remember that the centroid, Y bar, can be determined by using the first moment of area and divided by total area. So what I did, I already broke this guy into two pieces, the web and the flange. And remember, I need a reference. So I picked this red axis here is my reference line, right? So I'm going to determine the centroid with respect to this reference. Now remember that this is already symmetric with respect to y-axis or vertical axis, but it's not symmetric with respect to x-axis. Okay, so where is the centroid? Let's go ahead and find it. So remember, this is called first moment of area. Y is what? Y is the distance from the centroid of individual shapes from the reference. So that's 3 inches. Times what? Times the area of the web. What is the area of the web? Is 6 by 1, 6 inches squared. So this is in inches, this is in inches squared. Plus, now this is a typical mistake that everybody makes. You say, oh, where is the centroid of the flange? Right here. At what distance that guy is from the reference. So the typical mistake is that you put 0.5 there, but it's not 0.5. is with respect to the reference. So that's actually is 6.5. So be careful, guys. 6.5 is this y here times the area. Area is 8 by 1, 8 inches squared. Divided by total area, 6 for the web, 8 for the flange. If you do the calculation, this comes out to be 5 inches exactly. So let me pause the video for a second here, guys, and redraw this for you and show you how you can find the moment of inertia with respect to now this new axis. What axis I'm talking about? This axis. So now we know the centroid is 5 inches from what? From the reference line. So I'm going to pause the video for a second and come back and show you what's going on with the moment of inertia. Okay, guys, so now I drew the web and the flange, and I also brought the equation for moment of inertia of a rectangle with respect to the centroidal axis from the last page. Okay, now look, guys, all I have to do now is, in order to find moment of inertia, my objective is to find moment of inertia. Let me call this actually x-axis, the green axis. So I want to find moment of inertia with respect to this x-axis, green axis. So how do I do that? So I broke it into a web and a flange. So go ahead and find the moment of inertia of the web with respect to the green axis and moment of inertia of the flange with respect to the green axis, and then add them up. And that would be the moment of inertia of the T with respect to the green axis. Now, a minute ago, you guys remember, right here we had what? The parallax equation, I equal I bar plus AD squared. That's the equation that I'm going to use. I equal I bar plus AD squared. This I is the green axis. I want to transfer from where? From the black here to what? To the green axis. And I know that I bar for each one of these is 112 BH cube. Of course, B and H would be different for the flange and the web. So let's do it for the web first. So I for the web would be I bar plus AD squared. What is I bar? 112 BH cube plus AD squared. So let me go ahead and plug in. 112 what? B is 1 right here. H is 6, right? Plus area of the web is 6 inches squared. And what is D? This distance, if you know, this is 1 inch and this is 3 inches because it's right in the middle of the the centroidal axis, right in the middle of the web. So this would be 2 inches. That's your D. So 2 is squared. So if you do the calculation, this comes out to be 42 inches to the power 4. Okay, that takes care of the web. What about flange? Same story, guys. I bar plus AD squared. I bar 112 BH cube plus AD squared. BH, A, and D, they're all different. Now we're talking about this guy, the flange. So 112B now is 8, H is 1, right? Plus the area, 8 inches squared, area of the flange. Distance, what is this distance? Happens to be 1.5. 1 inch to here and half of the one here. If you do the calculation here, this comes out to be 18.67 inches to the power 4. So now we say I with respect to the green axis, I sub x, this guy, is equal to what? I of the web plus I of the flange. So that would be 42 inches to the power 4 plus 18.67 inches to the power 4. That becomes 60.67 inches to the power 4. So you see how, guys, we use the moment of the parallax equation, parallax's theorem, to be able to find moment of inertia with respect to the centroidal axis. Of course, we had to go and locate the centroid first, the 5 inch. Okay, so what I'm going to do, guys, now I'm going to stop here because I want to keep this under 10 minutes. And then I'll come back with another video. I'm going to use this cross section, which we've already calculated the moment of inertia, and we have located the centroid, and then continue with some type of loading. And then I will show you how we can actually calculate the bending stresses. As always, thank you for watching and listening, and keep yourself healthy and safe. See you soon.